Um, okay, the recording started, so maybe I say this again. Here we have um, this starting word. This is like a preview of what I'm going to talk about. We have some kind of starting word, and then we map it by some non-trivial morphism, here shown by these arrows. And here a non-triviality means at this stage injectivity. And this non-repetitive word happens to map to a cube. And it's quite interesting that this can even happen at all. Um, and we want to like see how common it is, and can we have a larger value than cube here? How this happens in non-trivial manner. So the talk is in 4 parts, basically 3 parts, because the last one is just conclusions and references, basically 1 slide. But I have some notation here, and then the question statement. And then I will talk about exponents of finite words, and then exponent of infinite words. And then, yeah, conclude with references. And I assume the basics are familiar to everyone, but here is some very basic things in the 1 slide. So first of all, how we take powers of words is that we start with a base word, and then we have some natural number n, and then we have a fraction which is the n divided by the length of the base word. And then we can take the v to the power of r, which is the prefix of length n of the infinite word v. So for example here, ABA to 7/3 would be just length 7 word that repeats the ABA shown here. So this is like first very basic thing that is relevant to the talk. And then we have morphisms. Everyone knows what those are, but yeah, there are maps with the rule where the image of uv has to be the image of u concatenated by the image of v. And we thus get that morphisms are defined by the images of letters. So we just replace every occurrence of a letter by its image. And yeah, since I talk about injective morphisms, I mean on finite words. So we can apply the morphisms to infinite words, but injectivity is only checked on the finite words. At some point, I will talk about situation where I have two-way infinite word that has 2 pre-images, even though the morphism is injective. Obviously, it's not injective then on the 2-way infinite words. It's injective on the finite words. In the whole talk, I will ignore the fact that injectivity checking is not necessarily trivial. I will just ignore that. You have to just believe me that the morphisms are injective when I say so. And yeah, in the binary morphisms, this is not a problem because binary morphisms are injective if and only if the images of letters are not whole number repetitions of some common word. This is by the defect effect. All right, so this is the very basics, and more important definitions for the talk are these exponents. So they are like the main thing on this talk. So we have 2 exponents for finite words and 2 for infinite words. First, we have the fractional exponent of finite word here. It is the maximum of the fractions that can be used in writing our word v here. So v is u to the power of r, and we take r as large as we can. And then the integer exponent is the same, but now the maximum is over natural numbers. So we have like full repetitions. And yeah, if I say only exponent in this talk, I will mean the fractional exponent. So it's like the normal exponent in this talk. Usually it's other way around, where the fractional exponent is like the more like it's like not the normal one. The integer exponent is the normal one usually. But in this talk, we switched it around. And then for infinite words, we have these two exponents. We have critical exponent. It's just the supremum of the regular exponents seen in the non-empty factors of the infinite word. And then we have the asymptotic critical exponent, which I will only say ACE for short. It is the limit supremum of the regular exponents when the factor is getting larger and larger and larger in size. So that's where the limit is. It's here at the n. And the point of these exponents is to measure, like with an explicit numeric value, how repetitive the word we are talking about is. Okay. And I just give some context on the asymptotic critical exponent, because if some of this exponent is not as familiar to you, I guess it's the asymptotic critical exponent then. So the idea of this asymptotic critical exponent, to like my understanding, started with this theorem of, I'm sorry about my pronunciation of the names. We have the Entreigen, Jackson, and Sutz in 1974. They proved the existence of infinite binary words that have no squares of length larger than 4. So basically, this is to my understanding, the first instance where repetition avoidance question was considered on infinite words where small factors were ignored. So asymptotic critical exponent in the definition is seen that, okay, we ignore all the small factors and we consider only the like a large picture of the word, how much those repeat. Yeah, and it's basically started here, I think. And then 10 years later, Beck showed that there exists an infinite binary word with age value equal to 1. And obviously that is an extreme value. You cannot get smaller than 1. And it's somewhat difficult to get your head around how does these words work, but they exist. And luckily, Kazan in 2008 effectively constructed one of these words. Not the same as Beck showed existing, but we have a construction of ace equaling to 1 word. So that's just some background. And yeah, then our explicit questions would be like this. So we want to have given a word as, can we design a morphism that maps the word to a large repetition? And then especially which words have an upper bound on the exponents after mapping via morphisms. So yeah, because the exponents are like measurements of how repetitive the word is, we want to know if there is an upper bound. And obviously, if we can use any morphisms, then obviously we can just take a periodic morphism. But if we strictly applies restrictions on the morphisms, then then these are interesting questions. So, and we chose injectivity as our definition of non-triviality at this case. Yep. So we define these new exponents. I don't know if exponents is good name for this, but we call this mapped exponents. So we have mapped exponent of finite word, we have mapped integer exponent of finite word, and then we have mapped a's of infinite word. And these are just supremums of the relative exponent when the argument word is mapped via arbitrary injective morphism. And yeah, Saarela started the study of this with this mapped integer exponent. So Saarela has like solo paper, which is also preprint about this mapped integer exponent. In this talk, I will mostly talk about the mapped fractional exponent and mapped a's, and I will touch a little bit on the mapped integer exponent, but I haven't worked on that much, or like I have worked on these two exponents far more. And yeah, we had 4 exponents previously. Now we have 3. So we could also define the mapped critical exponent. But since the critical exponent, if we have the same form for this definition, it would always be infinite for all infinite words by just mapping like some letter to a large repetition of itself. And the critical exponent like sees that, okay, we have n power here, so it will not ignore the fact that it's only a image of single letter. So this is not interesting exponent in this setting, but if you restrict your morphisms even more or in some alternative ways, then maybe this could also be considered, but for us, it's not interesting right now. And yeah, then if everything is clear for this point, then let me go to the exponents of finite words right away. Yeah, so here's the first basic example where the mapped integer exponent and mapped fractional exponents are both infinite. So we have this ABA squared word. And for this, we can design this morphism that fixes A and then maps B to B, and then we repeat AAB for k times, where k is like free parameter that we have here, a natural number. And then if we use this morphism on our word, we obtain a repetition of ABA once again with integer power here. And since the k is like free here, we see that, okay, the mapped integer exponent and the mapped fractional exponent at the same time are both infinite for this word. Very basic situation. And then if we take this last A away from our word, then we can very easily see that with the same morphism, we still have infinite mapped fractional exponent. Just because we only have taken our last A away. So the same morphism maps this still to a high fractional repetition of ABA. However, next slide shows that the mapped integer exponent of this new word here is 1. So it goes like this. So actually it's quite a bit older theorem that what what we are now working on. So in 1976, Spener and independently some others, but I think this is the earliest result of this thing. They proved that if our word is binary and primitive, then if both of the letters occur at least twice, then the mapped integer exponent is exactly 1. So you cannot have even a non-primitive word as a image under injective morphism in that case. And this is the only case where the mapped integer exponent of a binary primitive word is finite. So basically for primitive binary words, the mapped integer exponent is either 1 or it's infinite. And yeah, almost 50 years later, Sarah noted that, okay, we have a very similar situation for, and obviously this notation was not invented in the 1976, so I have like collected the theorem to fit our notation here. And then 50 years later, Sarah showed that, okay, if we have any primitive word, if every letter occurs on at least twice, then the mapped integer exponent is finite at that point. And then it actually has this nice upper bound. The length of the word is the upper bound at that point. Obviously, this statement is much bigger than the binary case statement, so we are working on the middle part here. But in terms of characterizing the words that can be mapped to arbitrarily large integer powers, this Sarah's theorem does it completely. It's very easy. You must have one letter that occurs only once. Okay. Then we didn't have example of a word where mapped fractional exponent is finite. So let me introduce one of those examples with this theorem. So all words of length less than 6 have infinite mapped fractional exponent. This is something that you can just check by like checking. And but then on length 6, you have some words that have finite value, and one of them is this AB, AB, BA. It has a value of 3, and it's a part of this set of words that we can compute the exact value of the mapped fractional exponent. So if we have AB repeated at least twice, n times, and then BA, then its mapped fractional exponent is 1 plus 2 divided by n minus 1. And I'm going to prove this because we only need theorem of Feynman-Wilf. And even like we don't even need this greatest common divisor part of it. So famously, theorem of Feynman-Wilf says that if a repetition of U and a repetition of V have a common prefix of length at least of length of U plus length of V, and we ignore this, then U and V are integer powers of common word. And this is enough to like calculate the exact value of this exponent here. So how it goes, we first of all show the upper bound. So let me take arbitrary injective morphism such that our word maps to some repetition of some primitive B. We can always choose the base word to be primitive if we consider like the largest R that we can have here. And yeah, by this assumption and the form of our word and the properties of morphisms, we have that there is a repetition of image of AB and the repetition of B. They have a common prefix of length, this image of AB repeated n times, just by this assumption. And if this is a longing of length, then, so at least this value, then the theorem of Fine and Wilf states that these words, the image of A, B, and B, are integer powers of common word. And since V is primitive, we have that the image of AB is V to power of M for some integer M. And then we can apply this equality to our assumption here to obtain this. And then we can cancel out the full repetitions of V to get that the image of BA has to be a fractional repetition of B. But obviously it is of the same length as the image of AB. So at this point, we can conclude that they are the same. The image of BA and the image of AB are the same. This contradicts the fact that, okay, we started with the injective morphism. And to avoid this contradiction, we must have that this common prefix that we have is small enough in length. So we have this inequality of lengths that we can rewrite in this form. And at this point, we can use this inequality of lengths in the definition of the R here. And yeah, we just get this upper bound, strict upper bound on the R, which is the exponent in image of U when the H was arbitrary injective morphism. So as a supremum, we get the upper bound like this. And then we check that the upper bound is actually reachable. So it must be reachable from below because we needed the supremum to get the possibility of equality here. But yeah, this is just found by computer search. So there's no like explanation of where this morphism comes from. But anyway, we map A to repetition of AB k times, and then end with A. And we map B to BA. And then just calculating, if we take our word and map it by this morphism, we get this gnarly looking repetition with this particular exponent. And yeah, taking the limit k tends to infinity, we get exactly the same number for the lower bound as we get for the upper bound. And we have our theorem. And this is also an example of words where we get arbitrarily close mapped fractional exponent, arbitrarily close to 1. So the value of 1 is not reachable for any particular word because we can always like introduce a little bit of repetition on the suffix from the prefix, like just altering the 1, like the last letter. So the value of 1 is it is not reachable exactly, but we can like get arbitrarily close with long words. Yeah, so this is an example of set of words where we can compute the mapped fractional exponent exactly. And then we wanted to try to characterize the words with infinite mapped fractional exponent, since Saarela was able to characterize the ones with infinite integer mapped integer exponent. And yeah, in the integer exponent case, all alphabet sizes like work pretty similar. But in this fractional exponent case, we need to, well, at least the binary case is much easier than the general alphabet case. It might be that the like trinary alphabet is as difficult as all the rest, but the binary one is much easier. So we consider the binary case more closely in this talk. So yeah, if we try to characterize these words, first of all, we were able to prove that if a word has infinite mapped fractional exponent, this implies that some letter in the word must have a fixed factor between every two occurrences of it. So I have a figure of the situation in the next slide, but let me just go through this proof sketch first, so the picture has a little bit more meaning behind it. So if we have an injective morphism that maps our word to some large repetition where this exponent is at least length of the word, then some letter must have an image that is larger in length than the base word x here, just so that the lengths here are equal. If none of the letters have this, then this equality cannot hold by just considering the lengths. And then we have this common fact about combinatorics on words, where a conjugate of a primitive word can be a factor of its repetition in only obvious ways. So usually it's stated in slightly different form, where a primitive word can be a factor of its square in only trivial ways. So this is like just small step over that fact. And together, these two imply that each occurrence of image of A has like a fixed place within the repetition of X. The figure in the next slide will make this a bit more clear what I mean. And so if we have some in-between word between two occurrences of image of A, then the image of A U, where this is the in-between word, is a whole number repetition of some fixed conjugate of the repetition base X. And this goes a bit maybe fast. So you have to like fill in the blanks in your mind or go read our preprints to actually get how this happens. But yeah, this is just a sketch. And in the pre-image side, then after these observations, if there is two different words between consecutive A's, then we can construct words that contradict the injectivity of H. Here is like the figure of the proof. So in the image side, if we have some image of A occurrences here, and the image of A is larger than the repetition what that is happening here in the image side, then they have the fixed place within this repetition. So after some fixed word, we must have a new image of A in exact same place considered in the repetition as the previous image of A. And then this repeats as many times as like we have room in the image side. And then in between here, we will always have some conjugate to some integer power like this. And when looking in the preimage, if we have A in the preimage, obviously it's mapped to some image of A. So if, like in this example, in the pre-image, we have 3 A's here, then in the image side, we will have corresponding images of A. For example, like this. It may not be exactly like this picture, but it can be like this picture. And at this point, we can extract the A's and these middle words, this yellow and this, I guess, violet word here. This has some fuzzy lining here to make it more clear. And note that, okay, we can actually switch the ordering of this word, and the image side does not change at all. So this word commute under the H. And if we assume that these words are different and there is no letter A's in them, then this is already contradicting the injectivity of H. So there's a bit like as again, you need to like fill the gaps that I'm leaving here in the explanation in your mind, or read the whole thing. But this is how the proof goes. All right, and yeah. So basically, we have the necessary condition that if the word has infinite mapped fractional exponent, then there is some letter such that every occurrence of the letter has fixed like a middle word. And one way this happens is with these words where we have some fractional repetition of a word where there is only one A. So like UAV, where this U and V have no A's in them. And then we have R here. So this is one type of word where this happens, this necessary condition. And for these words, we can pretty easily come up with the injective morphism here that shows that, okay, words of this type have infinite mapped fractional exponent. And this is a step towards of finding all the words with infinite mapped fractional exponent. And yeah, another easy case or somewhat easy case is these words where we have this factorization, where we have some prefix W1 and then some suffix W3, and these are A3, and then in between every A we have the fixed W2 factor. And we assume that W1, W2, and W3 all commute. And in this case, we can map this W, this whole word, into something that is of the form of the previous slide. And obviously, we can combine injective morphisms to single injective morphism. So if we get to some previous case, then we can go through and map it to arbitrarily large fractional exponents. So here the morphism is like this, and the calculation is not really interesting. It uses the fact that this commute multiple times, and then there's one time where you need to know that, okay, these words commuting means that they are all integer powers of some common word. At this last point, you need to know that. But yeah, this is also like easy case. And in binary, these two easy cases cover up all the like possible cases. So basically, it shows that we had the necessary condition in binary words that in between every A's, there has to be fixed numbers of B, or in the between every B, there has to be fixed numbers of A. And here now the W1, W2, W3 are all either just B's or just A's. So we like completed the binary case of characterizing the words with infinite map fractional exponents. And yeah, for example, we have this AABB word, and we can map it by mapping B to BAA to get a fractional repetition of AAB. And then we can map B again to B, and then repeat AAB as many times as we want to get as large repetition of AAB as we want. This is how the binary case goes. And yeah, in general, we have something similar. So the commutativity of this W1, W2, W3 is a bit like it's more than we need. In binary, we always have it, but it's more than we need in general case. So we have this weaker condition, but we don't actually know how weak it is or like how easy it is to have this condition that how this W1, W2, W3 relate with having some morphism that makes these suffix comparable and prefix comparable respectively. But we are somewhat pleased by this theorem because of the second condition where if the word can be mapped to at least to a repetition where the power is length of the word, then we already know that, okay, we can go to infinite. And this makes like computer searches a lot easier. And we also have an example where we saw that, okay, this if we increase the alphabet size, like with the length of the word, like in parallel, then this is like a somewhat good like estimate of the lower bound after which we reach the infinite case. And yeah, there is an example word that shows that okay, we definitely need like some extra work over the binary case in like already in ternary alphabet. And last thing that I have for finite words is that I can compute exactly some values of this mapped fractional exponent, but I have no general way of doing it, so I go case by case analysis. But it seems that I can do it by like there's like an almost general way of doing it, but not quite. So here's like values of some small words that have finite value, and I have computed these. And I think only the AB, AB, BA that I proved in this talk is something that you can read from the preprints. But yeah, these other values can be also computed. That's what I had for finite words. I will go faster on the infinite words, so no worry. Any questions about the finite words at this point? Obviously, we can go back after the conclusions. Yeah. So yeah, then on infinite words, this is like completely separate question, but there's a common element of injective morphisms, and then we have some kind of exponent that we are looking at. So here's the reminder of the definition of mapped A's. So is the limit supremum of the exponents that we can find in the finite factors of our word after it's mapped via arbitrary injective morphism. So, and the factors are getting larger and larger and larger and larger. And as it is the case often with infinite words, it's a bit difficult to give like good examples of this situation. In a sense that at least in the asymptotic like properties, we cannot look any finite path to get a feeling of how the asymptotics like work. In some particular words, we can look at the like structure of the small words and get the feeling of large words, but this is a bit trickier to give an example. So I have this example that once again you have to like fill the gaps a little bit for me to make this example work. So we start with the binary word, infinite binary word, with the A's value equal to 1. So it was proven, or I had the theorem at the start of the talk where it's proven that these words exist. And then if we factor it so that we have larger and larger factors here, and then we also take a copy of it under a different alphabet. So here, like A is 0 and B is 1. And we concatenate these factors in this sense where we have these like hidden squares in our word. So this is I don't actually know how this word would go, but example would be just like this A0, AB01, ABA010. So we have these like squares, but obviously they are not squares. And if we started with a word with A's value equal to 1, then it's not hard to believe that after this concatenation trick, we still have A's value equal to 1. But now because we have these hidden squares here, we can define this uniform morphism, injective morphism here, that like reveals the hidden squares in our word. So A maps to AC, 0 maps to CA, B maps to BC, and 1 maps to CB. And the effect of this is that if you take the hidden square and map it with this morphism, you obtain almost complete square. And when the hidden square gets larger in length, then the result will be closer and closer to actual square. And yeah, so we can, at least in this example, make the A's value larger with injective morphism. And even this is somewhat difficult to see because on binary words, it's very difficult to increase like if you take your favorite binary word, I would guarantee that it's very difficult, if not impossible, to increase the A's value with injective morphism. And yeah, then for general results, well, after that example, we wanted to once again see if we can characterize the words that have the infinite exponent value with this A's, mapped A's. And on these infinite words, it's much like like neater result maybe, because the mapped ace of infinite word is infinite if and only if the regular ace is already infinite. So basically, if you can do it by identity morphism. And we also have this explicit upper bound numerical value of mapped ace in terms of the regular ace, but I don't. We are basically certain that this is not a good upper bound, especially because there's quadratic term on the alphabet size, and we think that it definitely should be linear, but it's good enough to show this infinity result. So at least it has that going for it. Yeah. And let me be very fast on the binary case. So in binary case, we can actually have a lot better upper bound of the mapped ace in terms of the regular ace. Huge contribution towards this is this theorem by Dvorakova, Osem, and Obosenska recently in 2024. They had sufficient conditions where the injective morphism does not change the ace value at all. So it is that if the word has uniform letter frequencies and then all factors of the image word are large enough factors of the image words are so-called synchronizing words. I will explain in the next slide where this figure. Then the ace value does not change under this H. And then we basically modify this theorem by taking the uniform letter frequencies away. And then we have weaker statement where if we once again have the synchronizing words, then the ace value under this H is upper bound by the ceiling of the regular ace. And also, if we look closely to the binary case, we can squeeze this small positive constant here to make this inequality in the case where we have non-natural number ace value. So this lambda u does not depend on the h, it depends only on the binary word. And what are these firsts and how are they related to repetitions? The absolute certainty, we can see a letter boundary in the pre-image side. And if this word repeats, then this point also obviously repeats, and then we have always new repetition, new letter boundaries in the pre-image side, like this. And then these middle words here map to something similar always, and by injectivity they are the same. So this way, like synchronizing words, repeating synchronizing words like make so that the pre-image has to also have some kind of repetition there. But in the actual proof, the situation is a bit more complicated than in this figure, because actually we need to consider in the image side that we have several synchronizing points here and see what happens in the pre-image side more carefully to get exact result. If you use only like this image here, then you would get weaker result in the theorem. And yeah, why are the synchronizing words so good in the binary case? It's because if we have non-synchronizing factors that are larger and larger in size, then we are in the case where the age value is infinite. And this is just so that how this is obtained is that we get the limit word of these non-synchronizing factors in a way that we obtain two-way infinite word. And since they are not synchronizing, it means that we must have two disjoint pre-images for this infinite two-way infinite word that we obtain as a limit point. And yeah, there's older result by Karhumäki, Manuk, and Plavdowski that show that okay, then this limit word has to be periodic. Yes, and since it's a limit word of some kind of factors of our original word, then and it becomes periodic, then we must have that originally our word has a arbitrarily large like periodic parts. So the age value is infinite. You can ask questions if this is not clear. I must move on. And this is what the binary result is. So the mapped age value is equal to the regular age value if the word has integer age or it has a uniform letter frequencies. And in other cases, the mapped age is strictly upper bound by the ceiling of regular age. And this is just that, okay, we have always, if the age value is real number, then we always have synchronizing on large enough factors. And then we can apply either the theorem by Drovakova, Osem, and Oposenska, or our modification of it. And we get this nice result. And we have shown that this is the best you can do with only knowing the regular age value of your word. So we have construction to show that this is an exact theorem. And yeah, that's all that I have. So here's some conclusions. We have finite words with mapped exponent being arbitrarily close to 1. If the mapped exponent is infinite, then we have this kind of factorization. And similar factorization works with the mapped integer exponent being infinite, but then the k is 0. And in binary and in the integer exponent cases, this is complete like characterization. And in infinite words, the mapped ace is finite, if and only if the ace is finite. And in binary, we have this like exact upper bound conditions. Yeah, thank you. I guess now it's time for questions.
Thank you very much. Hajime, you have a question?
Yes, thank you for a nice talk. May I see the conclusion, the previous page?
Yes.
Yes, in this first line, one is accumulation point of EI.
Sorry?
So can you listen to me?
Yes.
So first conclusion is that one is accumulation point of EI. One is the accumulation point of the image of EI. So my interest is another accumulation point.
I would guess that, well, yes, there must be like a lot of those, but I haven't like considered that question fully. I would guess that you could like, I'm almost saying that you can make any fraction accumulation point. it feels right to me, but I haven't looked. It might be that there's something unintuitive happening there, but that's I'm almost certain that you can have an infinite number of accumulation points there, and I would say that most of the fraction is a accumulation point, but I'm not. I cannot like state that as a fact right away.
Okay, thank you. It's another work. Thank you.
Yeah. Yes.
Are there any other questions? So there's some old results on like critical exponents of fixed points of morphisms that say something like if your fixed point has a finite critical exponent, then the morphism has to be circular, which basically means that it has a bounded synchronization delay. So it sounds very much like the same kind of idea as what's going on with your results, where you need finitely, all but finitely many words are synchronizing. Is it kind of similar?
Yes, it is like very similar, even in the sense that I tried to look into this result and see that, okay, can it even be that our result like some kind of directly comes from this in if you just like replace some like assumptions like in a easy manner in a sense, but there was enough like differences where it doesn't really, or how do I say it? Iterating morphisms situation is a bit more you like know what's happening, whereas here because we consider like arbitrary, or like let me take the binary result for example. Our infinite word in the beginning can be anything. It's like a very wild situation in a sense, and when you are iterating morphisms, you sort of know the structure that you are ending up with. Obviously, it's a complicated result situation that has been studied a lot, but these results, arbitrary like binary words, can be very wild is what I'm gonna say about that question. Yes.
That makes sense.
Yeah.
Okay, are there any other questions? Okay, if not, thank you very much, Alex.